to be hosting this webinar today on algebraic reasoning. As Ben said, my name is Ruth. I'm at Lakehead University. I'm at the Aurelia campus. I'm looking out, gorgeous day today, looking out over Lake Simcoe. So I hope wherever you are, it's also a gorgeous day so we can all start to think about spring. Anyway, getting into our algebraic reasoning. So today's presentation is really going to be thinking about how we can support younger students to think algebraically. So one of the things that we talk about when we talk about early algebraic reasoning is the fact that we're not asking younger students, say students in kindergarten to grade 6, to start doing algebra. When we think about algebra, we tend to think about solving for x or balancing equations. We're not asking students to do that. What we're doing is thinking about introducing algebraic concepts early in their education so that they can develop these foundational thinking skills in elementary school so that when they transition to secondary school and hit formal algebraic instruction, they've got all of this really beautiful knowledge that they've built up. Um, so we're going to start with some definitions. This is from Maria Blanton and James Caput. And they define algebra as the process in which students generalize mathematical ideas from a set of particular instances, establish those generalizations through the discourse of argumentation, and express them in increasingly formal and age-appropriate ways. The two things I'd like to highlight about this definition is thinking about the discourse of argumentation. So having kids, supporting kids to really engage in intellectual argumentation in elementary grades. And we're going to look at some videos of student reasoning where we can start to think about how we can support this. And the other thing I'd like to point out with this definition is the idea of expressing generalizations in increasingly formal and age appropriate ways. So the kinds of generalizations that we're going to see in kindergarten are very different from the kinds of generalizations that we'd see in grade 6, which are different from the kinds of generalizations we'd see in secondary school. The next definition, so algebraic thinking or reasoning involves forming generalizations. So there's that really key idea about generalizations. We're going to be talking a lot about generalizations this morning. From experiences with number and computation, formalizing these ideas with the use of a meaningful symbol system, and exploring the concepts of pattern and functions. And the reason I highlighted that part of the definition is because that is really going to be our focus this morning, thinking about working with patterns and how that can support functional thinking in young students. So when we think about patterns and functions, functional thinking is analyzing patterns to identify change and to recognize relationships between two sets of numbers. And again, if we think about functions formally and we go back to secondary school, that's not, we're talking about in elementary school getting kids to recognize these relationships between two sets of numbers, but not in the kind of formal way that we do in secondary school. So why do we work with patterns? We do a lot of work with patterns. They're accessible to most students in kindergarten to grade 12. They're a tangible way of thinking of mathematical relationships. And also kids really love patterns. We are born as human beings to think in terms of patterns, to notice patterns in our world. That's how we function. And kids really love the orderliness and the predictability of patterns. And they're fun. They're fun. It's fun to build patterns and it's fun to analyze patterns. Another reason that we work with patterns is because we know from a huge body of research, not just the research I've done on this, which spanned about 7 to 10 years, but research that's been going on globally, we know that students who work with visual patterns and diagrams are more successful at understanding algebraic relationships, finding generalizations, and offering justifications than students who are taught to manipulate symbols or memorize algorithms. And this is hugely important. So the kids who actually work with these visual representations and understand them go on to do far better than kids who are just taught to memorize sequences of steps to solve an equation. So here's a typical kind of patterning activity. This is, really ubiquitous in math textbooks. So students are really good at describing the patterns. So they're very good at identifying the structure of the pattern. So if we look at this pattern, we can see that from the first figure to the second figure to the third figure, what most students will say is that they can see that we're adding one blue block to each of those arms each time. So basically the pattern is increasing by 3 blue blocks each time. And they're also good at noticing that the red block in the middle stays the same. That doesn't change. Um, and then they're good at extending this to the next figure. So if you ask them what the next one would look like, they're very good at understanding that if we're following the same growth pattern, then you would add 3 more blue blocks. And that's really what we focus on. So a lot of times in textbooks, you'll see this as described as a start with 4, grow by 3 kind of pattern. The problem with just thinking about the fact that we're adding 3 blocks each time comes when we ask for a slightly further prediction for one of the figures further down the sequence. So for instance, if we ask for the 10th figure, what would that look like? If you're thinking only about adding 3 blocks each time, then to get to the 10th figure, you would have had to know the 9th figure and add 3 blocks. And to know the 9th figure, you would have had to know the 8th figure and add 3 blocks. And so in order to figure out the 10th figure by only adding 3 blocks each time, thinking about it only as a pattern that adds 3 each time, you have to start with the third figure and add 3 and then add 3 again and add 3 again and add 3 again until you get to the 10th figure. That's a lot of calculation, and there's, ample opportunity for calculation error along the way, but it's a lot of work to think about adding 3 each time to get to the 10th figure. The real problem with this kind of thinking, which we call recursive thinking, so thinking about taking the previous figure and adding 3 onto it, the real problem with this kind of thinking is when we ask for something like the 100th figure of this pattern. And I have been in situations where I've asked children the 100th figure of a pattern, and they've tried to figure it out using this add 3 each time. It's very cumbersome, and they obviously typically give up not long after starting, recognizing that adding 3 for 100 times is a lot of work. And then, of course, the other problem with thinking recursively, adding 3 each time, is finding a general rule. So how could we determine how many blocks would be at any of the figures in this pattern? Unless you know what the previous figure is, you can't. All you can say is that you would take the previous figure and add 3 to it, but you can't really formalize it as a generalized rule to describe the structure of the pattern. So the other representation that is ubiquitous in patterning and algebra instruction is the order table of values. The main problem with this, I mean, it is a lovely representation showing the relationship between 2 sets of numbers, which is what we determined functional thinking was. But the problem with the ordered table of values like this is that students tend to look only down the output column, and they determine the difference between the numbers in the output column. And then they're taught, or they figure out that if there's a difference of 3 between, say, 4 and 7, that means times 3. So then they look over at the input column, at the first value in the input column, and they think, okay, so I've got 1 times 3 is 3, plus 1 is 4. That's my rule. However, they've lost the whole connection about what that actually means. So they take what could be an interesting functional relationship representation and actually just turn it into arithmetic. And usually they just look at 3 of the values in the table. So they'll look at the difference between 4 and 7, for example, determine that's 3. That means times 3, not sure why. That's just something I've been taught. Look over to the first input number, 1. 1 times 3 is 3, plus 1 is 4. Boom, got my rule. But really, with no understanding about what that means. It's really funny with these order tables of values. There's a math education researcher in Oxford, Anne Watson, who's done a lot of research and meta research on different representations for teaching algebraic concepts to kids. And she refers to these tables of, instead of tables of values, tables of no value, because what she's determined is that if this is the primary representation that's used in teaching, that it really, really severely limits kids' abilities to develop these functional concepts. So let's recap some of the difficulties of working with growing patterns as they stand in a lot of instructional material that's around today. The route from perceiving patterns to finding generalized rules and other algebraic representations is difficult. Patterning problems can become arithmetic exercises with tables of ordered values, with literal understanding of that relationship between the sets of data, what that actually means. There's no clear connection between patterning activities and later formal algebraic instruction. And the connections among representations, patterns, pattern rules, equations, tables of values, they're not made explicit. So research tells us that when students are introduced to multiple representations, so linear growing patterns, graphs, pattern rules, and equations, they can develop a really deep understanding of linear relationships, of these functional relationships. And it's the exploration of the interaction among different representations that really helps develop this deep understanding. So we're going to start with one activity that's really lovely to do with kids. Usually when I do these sessions face to face with people, I model what it looks like in the classroom, and so we're going to try and do that today. So we set up an input and output table, and we play a game called the robot game. And a really nice way to introduce this in the classroom is for the teacher to come in and tell kids that today she's not their teacher, she's a robot. She's going to be taking in input numbers and using a mathematical rule, she's going to transform them into output numbers. And it's the job of the students to figure out what rule she's using. And so the really important thing for this activity is that students just call out numbers between a set of parameters. So say numbers between 1 and 10, numbers between 1 and 12, whatever the students are comfortable working with. So we're going to simulate this now. So let's say a student calls out 6. So you as the teacher are modeling, okay, I'm going to take the 6, I put it in my head to transform it, and out comes 18. And then the next number going in, somebody calls out 4. And then you model taking that in, and this time you ask your students to predict in their minds what they think the output's going to be. And the output is 12. So you ask for another input number. Somebody says 9. This time you ask them to turn and whisper to the person next to them and predict what they think the output number is going to be. And it is 27. And then the final thing, somebody calls out 12. And again, you want them to predict, and this time you're asking them to predict, but also explain why they think that that is going to be the output. And then it's 36, and then you ask for anyone to tell you what they think the rule is. And we have a really specific way of stating the rule. So the rule is the output is equal to the input times 3. So the really powerful thing about this, and if you do this in the classroom, it's lovely because the kids are so engaged. One, because they're giving you the input numbers, and you're also giving them, opportunity to predict with their friend what they think the output's going to be, and they're trying to figure out what's going on. But the really lovely thing about this, if you look at the table that's created, it's unordered. So you can't just look down that output column. You really need to think about looking across at that relationship, at that numeric relationship. And we've done this activity as young as grade 2, starting with just times 2 rule. So the kids are thinking about doubling the number or adding the number to itself. And we've also gone all the way up and done this in grade 9 and 10 classes to really get them to think about what is happening between each of those instances of the input number and how we get to the output number. And so this is a great activity to do for many days until the kids are feeling really comfortable with it. You have students come up and act as the robot, and they can come up and bring a friend with them or bring a calculator or a multiplication table or whatever to make them feel secure up there to be the robot. And then you can have kids working in pairs, taking turns. One can be the robot, one can be the guesser, and then they switch roles. So there's a lot of scope for this. The other nice thing about this activity is it's one of those kind of self-differentiating activities, so the kids will work at levels that are suitable for them. So people who are working on, their multiplication tables can look at using certain kinds of rules, whereas kids who are like really ready to explore more complex mathematical rules can do that. So we start with just the rules with just a multiplier and do that until the kids are feeling pretty confident about what's going on. And then we introduce them to this. So somebody calls out 6, and my output is 15. And it's really interesting the first time you do this in a classroom because the kids will have gotten to the point where they're feeling very secure about understanding the robot rule game, and then this happens. Um, so we've got 6 and 15. Someone calls out 4. Again, you want them to predict in their minds what they think is going to happen. And we get 11. And then we get, oh, this is lovely. Whenever somebody guesses an input number of 0, it's lovely. And we'll talk about why that is. So this time the output is 3. And then somebody calls out 10, another lovely number. And this time the output is 23. And so then you ask again for the rule, output equals input times 2 plus 3. So again, the lovely thing about this is you're giving at least 4 input-output pairings. And the teacher can gauge where the students are at if they need another one in order to guess the rule, if everybody seems ready with just 4. It's important to keep going with that to the point where you think that most people are pretty solid in their understanding of what's happening. And also having that predicting part. Like we talk a lot about the importance of predicting in math because it really engages students in what's going on if you ask them to predict. Especially after the first pairing, if we're looking at 6 and 15, they might have different sorts of rules that they're thinking about it could be. So they're predicting it could be this or it could be this. And then by the second input-output pairing, they're starting to revise those initial conjectures, which is really nice. So this rule has both a multiplier and an addition part to it. And again, you'd have, several of these examples, and then you'd have the kids work together in pairs, one person being the robot, coming up with the rule, the other person guessing. And as students play this rule or this game, they start to come up with some realizations. So one of the realizations they come up with is that 0 is a really lovely input number. Because if you have an input of 0, if you've got a rule that has a multiplication part and an addition part, putting in 0 wipes out that multiplication part. And so you're only left with the addition part. And then you can go back to some of the former input-output pairings, subtract 3 from 11, for example, to get 8, and then divide 8 by 4, and that gives you the multiplier. So there's lots of really nice, even though this is a way of getting kids to think about those functional relationships, there's also a lot of really nice number sense enumeration thinking that happens during this as well. And then interspersed with those kind of numeric activities, we then alternate them with more visual activities because we found in our research that usually about half the class are numeric thinkers. They really like looking at number patterns and they understand numeric relationships. But about half the class are more visual thinkers. They prefer to explore mathematics visually, and it's combining the two that is really powerful. So we start off with building some patterns, like this growing pattern. And the really important relationship that we emphasize with this pattern is not so much the fact that it's going up by 3 each time, but we really emphasize the relationship between the position number and the number of tiles. So we see that at position 1, we have one group of 3 tiles. At position 2, we have 2 groups of 3 tiles, or 6 tiles altogether. And at position 3, we have 3 groups of 3 tiles, or 9 tiles altogether. And then we would ask students what would come at position 4. 4 groups of 3 tiles or 12 tiles altogether. And if they get that relationship, if that is emphasized and you really spend a lot of time focusing on the fact that that one tells you how many groups of 3 tiles we have, then it's very easy then to think about how many tiles would be at the 10th position. The 10th position is 10 groups of 3 tiles or 30 tiles. And then it's easy to think about the 100th position. So at 100, we would have 100 groups of 3 tiles or 300 tiles. And then the 1000th position, so we'd have 1,000 groups of 3 tiles, so 3,000 tiles. And it's once that connection has been made and you start to do these far predictions with friendly numbers, it's really exciting for the kids because that's very, very powerful thinking to be able to make those very far predictions and know that you're correct because you know that position number is telling you how many groups of 3 there are. So even for students who are still even struggling with their multiplication, they can at least tell you that, say, at the 25th position, it would be 25 groups of 3 tiles, and then they could figure out how many those are. But even understanding that the 25th position has 25 groups of 3 tiles, and they can picture or visualize what 25 groups of 3 tiles would mean, that's really powerful thinking in itself. So this helps us to think about, again, that relationship. So in this instance, because we're not using input and output numbers, we're using position numbers and numbers of tiles, our rule is a little bit different. So our rule in this case is the number of tiles is equal to the position number times 3. And you'll see that it's really similar to our output and input rule. So instead of output equals input times 3, it's number of tiles equals position number times 3. So the number of tiles represents our output number, and the position number represents our input number, and the times 3 is our multiplier. So that drives the relationship between the two. So the other really nice thing about this activity, once we've done it for a while, so having kids think about rules and building different rules and guessing each other's rules, is we found that what we weren't expecting, but we should have probably anticipated, is that not only did it really help with kids developing an understanding of functional thinking, it also really helped with their multiplicative understanding. And this is because it's a really nice way for kids to think about unitizing. Unitizing is one of the most important concepts when developing an understanding of multiplication and multiplicative thinking. So unitizing is the ability to think of one unit simultaneously as one unit, and in this case, 3 tiles. So it's understanding one unit is one unit, but also it's the number of elements that make up the unit. And so in this example, we have at position 1 unit of 3 tiles. Position 2, there's 2 units. And position 3, there's 3 units. And it's the process of building patterns and creating these units that are then replicated according to the number on the position that really help students to develop that understanding of unitizing. Also, as they're going around and guessing other people's rules for their pattern, they are analyzing the structure of the pattern, relating the number of tiles and the physical structure of the pattern with the position number, and through that analysis are able to come up with the rule. But that process of analysis is really, really powerful for developing an understanding of multiplication. So we do some activities, just having kids think about building rules that only have a multiplier. And then we introduce something like this. So at the first position, I have 2 blue tiles and 3 red tiles. Position 2, I have 2 groups of 2 and 3 red tiles. And position 3, I have 3 groups of 2 or 6 tiles and 3 red tiles. And so again, asking students to predict what would the 4th position have. 4 groups of 2 blue tiles and then 3 red tiles. And then thinking again about the 10th position and then the 100th position. And by asking for those next, near, and far predictions, so the 4th, the 10th, the 100th position. That's what stops kids just from thinking about adding 2 each time to really thinking about that relationship between the position number and number of tiles. So for this rule, again, because we're using tiles and position numbers, the rule is the number of tiles is equal to the position number times 2 plus 3. And you'll see what we've color coded that because the multiplicative part of the rule, the multiplication part of the rule, tells us the growth of the pattern, how the pattern is growing. And the addition part tells us what stays the same. And it's really nice for students to think about, well, what's another way of saying something that stays the same? It stays constant. So the addition part is what remains constant in the pattern. And this is then we have activities where we give kids rules and they take the generalized rule that we give them and they have to build the pattern. And then they hide their rules because they're secret rules. And then they walk around, they do a gallery walk around the classroom and guess each other's rules. And this is kind of what it looks like in the classroom. There's kids building all over tables and on the floor, and it gets very messy and very, very exciting. I'm going to ask you to look at this pattern and see if you can guess what's the rule. So you'll see on the bottom there, oh, look at you all, brilliant. So exactly right, this rule obviously is number of tiles equals position number times 3 plus 1. I really like this pattern because you can see how the students go from an array structure, which is how we model it, to then being more creative. So what this shows us is that at position 1, there is that group of 3 blue tiles plus the 1 yellow tile. So if we think about our rule, number of tiles equals position number times 3 plus 1. 1 times 3 is 3, plus 1 is 4. That's how many tiles there are. At position 2, we've got those 2 groups of 3 blue tiles. So 2 times 3 is 6, plus 1 is 7, and that's how many tiles there are. And at position 3, we've got 3 groups of 3, so 9 tiles, plus 1 at the top is 10. So we can see in this pattern, what the child has done has taken the rule, number of tiles equals position number times 3 plus 1, and built it out so that the blue tiles represent the times 3 part, and the yellow tile represents the plus 1 part at the top. Okay, let's do another one. Okay, how about this one? Just trying to see everybody's answers here. Okay, so this is, if we look at how the pattern is growing, and this is also a really beautiful example of how creative the students become with this. So if we look at this rule, we can see that the red part is growing. And so we've got 1 group of 2, then 2 groups of 2, then 3 groups of 2. And then we've got that lovely central piece in yellow that doesn't change, and there's 6 tiles there. So this is a times 2 plus 6. So we do quite a few activities using the 2 colors for the rules so that the students can really get a sense of the part of the rule that determines how their pattern grows, which is the multiplicative part, the multiplication part of the rule, and which part of the rule is responsible for what stays the same. So we have them do quite a lot of pattern building. not just pattern building and not just guessing rules, but also talking about the strategies that they're using, what makes it easier to determine a rule, what makes it more difficult, the fact that visually you have to have the same kind of predictability visually as you do numerically. So you can't just take a bunch of tiles and throw them down. And even though it's the correct number of tiles, like there has to be visually a pattern as well. So one of the ways that we have kids think about that is, could you look at a pattern and accurately build another position of that pattern? So for example, for this pattern, looking at this pattern, you could, if you recognize the structure of this pattern, you could accurately build the fifth position of this or the 10th position of this or whatever. And that's a really nice activity to do a bit later on with them, is to have patterns with missing position numbers and ask students to go around and complete someone else's pattern just to ensure that they are understanding their relationships. So once the students are very solid with their understanding of the two color patterns, we move to one color patterns. So this is an example of the first position of a one color pattern. It still has a multiplier, it still has a constant, but I'm only using one color of tile. And the reason we do this is because after the students have done, a few rounds of looking at the two color patterns and they're really solid with it's not so much of a challenge anymore. So we want to keep kind of upping the cognitive challenge for them. So for this pattern, there's all kinds of rules that this pattern could be following. So this could be times 2 plus 4. It could be times 4 plus 2. It could be times 6. It could be, let's see, times 1 plus 5. All sorts of different rules it could be following. And it's really nice to have students generate a lot of rules that this pattern potentially could be following. And then with the second position, we can think about which of those rules still holds true for the second position. And then if we look at the third position, we see 3 groups of 2 and 4 tiles. So we can be pretty sure that this rule is, oops, sorry, I thought I had written the rule down. This rule is the number of tiles is equal to the position number times 2 plus 4. So those plus 4, those 4 sort of squares that have been rotated to look like diamonds stay the same, and the groups of 2 in that array are growing by 2 each time. So we know that it's multiplied by 2 plus 4. And this is a nice to introduce because students have to kind of go back and forth between visually what they see is happening and numerically what's happening. So for example, if they looked at that first position and thought maybe it's times 4 plus 2, if they look at the second position, 2 times 4 is 8, plus 2 is 10, and then they count the number of tiles and find there's only 8, that doesn't work. So it's really nice, like they can make conjectures and there's back and forth between visually and numerically what's happening in the pattern. So here is a pattern that a student created. I think this was a grade 3 student. And so analyzing this pattern, let's see some of the conjectures that you have about what the rule is for this pattern. Nice. So this one is tricky. This is why I like this so much. Um, so for the first position, I'll just show you how the student was thinking about it. So for the first position, the student thought about the fact that there were 5 red tiles in the middle and then 2 tiles kind of on the outside edge. And then if you look at the second position, you can see that that group of 5 is replicated again. And then there's the 2 tiles. And then at position 3, we've got 3 replications of that 5 and then the 2 on the side. So again, it's really nice to go through some of the student conjectures and see if their ideas for what the pattern rule might be actually hold true for the number of tiles that there are. So for example, a lot of students, if they look at position 1 of this pattern, think that maybe it's a times 3 plus 4 or times 4 plus 3 because there's 3 tiles that are diamond kind of orientation. And then thinking about, does that rule give us the number of tiles that we need for position 2 or that are at position 2? And really underscoring the point that the rule, the reason that we call it a rule or a pattern rule, is that it holds true for any position of the pattern. So it will give us the accurate number of tiles for any position of the pattern. So these activities, all of these pattern building activities really help students further explore the relationship between the position number and the number of tiles at each position. And I've got a video to show you now. This was a video taken by a teacher in the classroom. So the audio is a bit rough on it, but I think that lends to its authenticity. And she was doing some of these activities in her classroom and had her, I think it was her iPad that was recording some of the students and some of their thinking. So the first little girl you're going to see, because it's quite quick, so I just want to set it up for you. She was asked to build a couple of patterns. She built one, and then her second pattern was just 3 position cards on an empty desk. And apparently she was done her pattern, and her teacher asked her what her pattern rule is. And she gives a very interesting explanation for what her pattern rule is. So we'll take a look at that video now.
I don't see anything here. Okay.
It's times 0 plus 0.
Times 0 plus.
I did a 3D pattern using golden bricks. There's 3 in the middle, going by 3 every time, so the multiplicative is always 3.
Okay. And so, what about, let me ask you if, how about on the 25th figure? How many blocks would you make?
Well, that's 25 times 3 plus 6.
Okay, so what would that be altogether?
1 second.
That's okay.
81.
Okay, and how did you figure out 8? Oh! How'd you figure out 80? That's okay. He can build it again. How did you figure out 81 so fast?
I just basically did 25 times 3, and 3 times 25 is just as easy.
Okay.
75 because 40s and such. Just
Sure.
plus
Yeah.
6. That was kind of simple.
It's kind of simple. So the first little girl, her rule, of course, I hope you heard that, was times 0 plus 0, which is a really smart way of getting out of doing any more work, I think, if you're done with pattern building for the day. And the second little guy, that really illustrated, first of all, the fact that these kids are making these really nice connections between position number of tiles so that they can make these far predictions, but also really shows the nice number sense that's coming up in these activities too. So asking for the 25th position, knowing it would be 25 groups of 3 plus 6, but then figuring out how many tiles that actually would be, going back to his understanding of 25 groups of 3 could be the same as 3 groups of 25, 3 times 25, and he knew that because of quarters it was 75, and then just add 6 to that. So it's simple, really. So lots of rich, deep mathematical understanding out of these activities. And then, so we have another activity once the students, again, once they're solid with building the one color patterns. And this is also, it's not only a fun game that the kids can play together, but it's also a really nice assessment for teachers to think about whether or not their kids are really making that connection between position number and number of tiles, if they're really understanding that functional relationship. So what we do is, for the assessment part of it, is we'd have this or another configuration of tiles at one position and ask the students to generate how many rules the pattern could be following based on that number of tiles at that position number. And then we move the tiles to another position number and see if they can recognize that if you change the position number, that necessarily has to change the rule that you're using if you keep the tiles the same. So we're going to look at what this assessment looks like with a little girl named Liga, who had this configuration of tiles that started out at position 2 and then was moved to position 3.
Well, the rule could be something like times 3 plus 2 because 2 times 3 is 6, and those could be these two, 3, 6, and then it could be plus 2, and those would be the ones that would always stay.
Is there any other rules it could be?
Yeah, I think, it could be, times 2 plus 4 because, 2 times 2 is 4, which could be those 4, and then, well, it doesn't really matter, but then the plus 4 could be those 4.
Anything else?
Um,
Those are really good.
it could be times 2 plus 6 because it doesn't really matter which 2, but 2 times 2, times 1 plus 6, sorry, because 2 times 1 is 2 plus 6 would be those 6.
Nice job. Any others?
It could be 2 times 4, like just 2 times 4 because, no, times 4 because 2 times 4 would be 8, and that's how many there are.
Nice job. Excellent job. So what if we did this? And what does that mean?
It's in position 3 now. So there could be, like, it could be times 1 plus 5. So 3 times 1 is 3 plus 5 is 8, and that's how many there are. It could also be times 2 because times 2 plus 2 because 3 times 2 is 6 and plus 2 is 8.
And can you see that?
Yeah, it would be, well, the 2 times 3 could be somewhere like that's one pair of 3, that's the other, so that's the 2, and then plus 2 is those 2.
Nice. So if you did that, what would it look like then in position 2?
In position 2, it would be the same thing except there wouldn't be these 2.
Very nice job. So what happened when I moved the 8 blocks from position 2 to position 3? What did that mean?
It means that it had to be a different rule because if it's in different positions, it has to be different because, like, say times 2 for the 2, it would be, well, it would have to be times 2 plus 4, but for this one, it wouldn't work because 3 times 2 is 6, and then plus 4, there aren't 4 left.
So I'm really interested. I'd like to take a minute or two. If you can just, if you're with a group, chat with them, or if you're by yourself, just to think about the kinds of thinking you heard coming out during that conversation. There was a lot of math thinking. So I'd love it if we could highlight a couple of things that maybe you heard. So we'll take a minute or two for you to just write some thoughts down. Yeah, so you highlighted a lot of really important things about this. So the fact that she could offer various answers and as Terry says, highlighting the fact that she can explain her thinking, she can tell why it is, which is like Angelo talking about the fact that she could go from a visual to a numeric pattern, so she could use the visual and the numeric and use that to explain her thinking. And she does have great flexibility in her thinking. Um, Really nice job as the Mackenzie Glenn PS team identified expressing her thinking. Great math vocabulary, a deep understanding of the relationship between the constant and the multiplier. Um, yeah, and the fact that it's lovely because when you get students to this point that understand that not only can they have very flexible thinking and think about that connection in different ways, and I think Terry also talked about it, it's kind of a backward sort of way because we tend to give patterns that are complete and have kids just find the rule, but to give them just one position and then move it around is really neat because that really challenges them and us to see that they really understand it. Um, so this is a really nice way for teachers to really see if their students are deeply understanding that connection because once you get to this point, you know that the students really deeply understand that functional relationship between those two sets of quantities. So I wanted to share this with you. So one of the things that we've been exploring is how very young students, JK and SK, can start to think about functional relationships. So they can begin to think about the relationships between position number and number of tiles and can use this to understand this understanding to make near, far, and very far predictions. And so I've got a video to show you now of a teaching sequence that I've tried out in a few kindergarten classes. And the nice thing is we always get the same results. So we're going to look at a video that shows um, a couple of the activities that we do with them. I'd like you to listen to the student thinking as we watch that. And then Also, you'll see an excerpt from one of the post interviews I did with one of the kids. So we'll talk about the instructional sequence a bit more after the video.
See these numbers down here?
1, 2, 3, 4,
5. Yeah. And what's going to happen with this pattern machine is or you guys are going to choose a number.
Quick fun.
I'm going to put it in, and the machine is going to tell us how to build the pattern. Oh, you're going to start with the 5. Okay, so we take the 5, and this says input. So it's input, so we put the number 5 in, and let's see what the machine gives us for the output. Here it comes. Wow. Look at that. I'm going to build that because that is like a plan for building. So let's count how many tiles I've got. There's 1, 2, 3, 4, oops, 5. 5 red tiles. Okay, what number is this one?
1.
Okay, so let's put this in. And again, I want you to predict, I want you to, I want you to guess how many tiles are going to come out. How many tiles is the machine going to tell us that we need? We put a 1 in. How many tiles are we going to use to count? Who's got an idea? How many people agree that it's 1 tile? The machine's going to tell us 1 tile. Okay, let's see if we're right. Let's see their output. Here it comes.
1.
Look, how many tiles?
1.
If there was a position 6, how many tiles would be moved? What do you think? Wow, how do you know that? Because after 5 it's 6. How do you know it's growing? What do you think?
Because it gets bigger and bigger.
Okay, now we've changed the machine, so we have to see what pattern the machine wants to do this time. There goes number 1. Let's see what comes out. Here it comes. Oh, look at that. How many reds?
2.
And how many blues?
2.
Okay, so here's a harder question. How many tiles are there all together?
4.
Oh my goodness, you are so smart. What's your prediction?
4 and
4 red and 4 blue? Right, so we put our numbers in. Does everybody remember that? We put these numbers in to the input, and then what came out of here?
Output.
Output. Tell me what number you want me to put in the function machine. Yes, what number?
5.
5.
That's what
Okay.
me and Jackson were before.
You were? Okay, so here goes 5. 5's going in. Here it comes. Oh my goodness, so how many red tiles do we have?
5.
Let's count them. 1, 2, 3, 4, 5. And how many blue tiles?
5.
Yeah, let's count them.
1,
2, 3, 4, 5.
4 red, 4 red, and 4 blue.
How many people agree with that prediction?
If you add the red and blue up together, it would make 2. And then it would make 4, and then 6, 8, 10.
Positions? At number 6, there would be...
6 reds and 6 blues.
Huh. What about at 10?
10, there would be 10 reds and 10 blues.
What about at 100?
100 reds and 100 blues. There's 1 red and 1 blue, and it makes 2. And there's 2 reds and that makes 4.
Did we? How many reds?
3 blue. It makes 6. 4 reds and 4 blues. That makes 5 reds and 5 blues. Make 10.
So how many would there be at number 6 if you were doing number 6?
6.
6 what?
6 reds and 6 blues.
Do you remember how many that was altogether?
12.
Oh, so smart.
10 reds, 10 blues, and 10 greens. 30.
Wow, nice thinking, my friend. Position 100.
300.
You came to that very quickly, didn't you? How about position 1000?
3,000.
Position 1 million?
3 million.
Wow. Wow, Nico. And what would that look like?
It'd be like all over this classroom.
Wow, that would be a lot of tiles filling our classroom for sure. How many would be at position 10 if I add yellow into my pattern?
40.
Wow. And how about at position 100?
400.
Nico, I think you really get these growing patterns, don't you?
So again, I'd love you just to chat what you saw and what you heard. And any questions? Yeah, so some interesting stuff there. Yeah, obviously, and this was true for most of the kids that we interviewed by the end could definitely predict to the 10th. And then about half of them could predict beyond the 10th to the 100th or 1000th. Um, and I like that Terry brought up a really interesting question. I'm not sure that they have an understanding of place value because place value is really about understanding the value of a digit in a multi-digit number, but he certainly has an understanding of multiples of 10 or multiples of 100. Um, and I love Angelo's comment about connecting the pattern to the physical space in the room, like thinking about what, 3,000 tiles or 3 million tiles would look like. Um, yeah, so we'll, oops, just go on. So just to briefly recap, we use the function machine pretty much like the robot game that we started off with this morning, but this is a much more visual way for kids to see an input number going in and then seeing the output come out, and the output was visual rather than numeric. And even though the input cards are chosen randomly, the output is placed in its ordinal position. So you've kind of got two of those kind of thinking going together. So it's not the kids pick up whatever input number they want to go. Usually they start with 5. They like really big numbers. But then as we're placing everything down, it slots into its ordinal position. And then they build their own patterns. And then they started to experiment with different kinds of growing patterns and then predicting the next near and sometimes the far positions of those. So then we're going to think about position 0, because we've really only been working with position 1, 2, and 3 so far. And if we look at any pattern that has a two-part rule, a multiplier and a constant, we can see that at position 0, the only thing that's represented is the constant, because you have 0 groups of whatever. So in this case, it's 0 groups of 3, but you still have your +1. So this is a really neat way to think about what happens when we multiply by 0, but also thinking about what part of the rule is represented at position 0. And this is where we start to transition into another representation, which is graphical representation. So the way that, well, first of all, let's talk about some difficulties with graphs. So and this is research done obviously with older kids, so we know that the connection between the value of the multiplier and the slope of the line and the value of the constant and the y-intercept, so where the line starts on the graph, isn't clear for a lot of students. They have difficulty predicting how changing the multiplier or the constant will change the graph. And students are really good at plotting points, usually because they construct that order table of values and then they just go through and they can plot the points, but they don't really see the resulting trend line on the graph as a representation of the same kind of rule that their pattern was representing. So this is how we introduce graphing after the kids have been doing lots and lots and lots of patterning activities. So we build a pattern like this. So this would be a ×4 pattern. Then we place a dot at the top of each of the stacks, and then we take the tiles away, and we have kids describe what this line of dots looks like. And you know, they generally point out that it's a straight line, that it's a straight diagonal line, that it seems to be the dots seem to be going upwards. And then what we talk about is that this dot is a representation of the number of tiles at position 1. This dot is a representation of the number of tiles at position 2. And this dot represents the number of tiles at position 3. But how can we show exactly how many tiles there were? So we think about the fact that we can show the correct number of tiles. And then we ask students, what is this starting to look like? It's starting to look like a graph. So when we're introducing these graphing activities, we do it very concretely. So we ask kids to choose any 3 pattern rules that only have a multiplier, to make the pattern with the tiles, and then to count the number of tiles at each position and make a dot on the graph. And then we ask them to think about what they notice about the trend lines. So this is what, in the background, you can see. These girls were very ambitious. They didn't just choose 3 rules, they chose multiple rules. And we have a conversation about what they see, like what does the trend line for tiles equals position number times 1 look like compared to a ×7 rule. So on their graph, you can see the ×1 rule is at the bottom of the graph, and the ×7 rule is that green line at the top of the graph. And they talk about the angle of that line, or the steepness of that line, increases, and they have a really good way of explaining why that is, because having built their patterns, they think about the fact that if you're looking at a ×1 rule, the pattern only increases by 1 block each time, so it's not increasing very quickly. Whereas if you've got a ×7 rule, it's increasing by 7 blocks every time. That's a lot more of an increase. So you're piling more blocks on top of each other. So it's really concrete, and we have them leave their patterns so that they can make connections between the patterns they were building and the resulting lines on the graph. And then what we do is we have them build a 2-step rule, or a rule with a multiplier and a constant. We have them build position 0, and when they're constructing their graph, position 0 is put right on that vertical axis there. So that's where position 0 is. So we do exactly the same thing. We give them a rule, have them build position 0, position 1, position 2, position 3 with the tiles. And again, they're just counting that number of tiles and plotting the points on the graph that represent the number of tiles in their position. So we can see this pattern here. If we look over at the graph, we can see at the position 0 on the graph, the vertical axis, we can see that a dot is at the third number of tiles. So there's a dot at number 3 representing the fact that at position 0, there are 3 tiles. And then there's at position 1, 5 tiles, 7 tiles, and 9 tiles. So it's really concrete at this point still. So what we do next is once students are fairly solid with that understanding, we give them 3 rules and we ask them to predict what the trend lines are going to look like on the graph. So the first set of rules we give them have different multipliers, but the same constant. And so what I'd love you to do now is to just, if you could describe or predict what you think the trend lines would look like on the graph. So there would be one graph, 3 trend lines. What would they look like in relation to each other? Some very nice predictions. So when we're doing this, when the kids are building their patterns, we ask them to keep all of their patterns. So build all 3 of the patterns and then graph them and then notice what happens so that they can explain their graphs. Very excellent. So what it looks like is this is an example of 3 of the patterns and then the resulting graph. And what we can see is that if you look at the position 0 of the patterns, we can see that they all have 1 tile at position 0. But if we compare the growth of the patterns, looking at the yellow tiles in each of the patterns, we can again see that the pattern on the bottom representing times 1, those yellow tiles are not increasing very quickly. Whereas if we look at the top pattern, which represents times 5, we can see that there's a lot more tiles there and that they're increasing at a much greater rate. And so it gives kids, because a lot of times they'll say, well, the line for times 5 is going to be steeper than the line for times 1, but they can't really explain why. And this gives them a really nice concrete way of explaining why that is, why we get that steeper slope with that multiplier. Also, because we're only using 1 quadrant of the graph, it's perfectly fine for them to talk about the line starting at 1 and then going up. So that's some language that you'll sometimes use. Jeff also said that the times 5 line would be higher. That's also language that we hear a lot from the kids, that it's steeper, it's higher up on the graph. Okay, so your next challenge is to look at these 3 rules and again, predict what you think those trend lines will look like. Very excellent predictions. I like that. Like there's multiple ways that that you have of describing what you're seeing, and this is so important when we're supporting student conversation in the classroom. Is even though one person might have the correct answer, quote unquote correct answer, it's really important to get other people to say their answer in their own words, so that for students who think they understand what's going on, it just kind of reinforces that with some different language. And a lot of times students will use gestures as well, which is really helpful. And for the students who are not quite grasping what's happening, hearing multiple iterations of the same idea but said in very different ways can be extremely helpful. So for example, the place where the graph touches the y-axis becomes higher, but they will all be parallel, and all would be going up the same rate but starting at different points on the y-axis. Lines will be parallel at position 0 and 2, one at position 0 and 6, and position 0 and 9, and all originate at different spots. All would be parallel. Like you said, basically the same thing, but in the differences in the way that you've said that is interesting, and I think really helpful for people to continue to build their understanding. So again, we have kids build the patterns first, keep those patterns, and then create the graph. And again, we can see at position 0, if we look at position 0, we can see that that constant is different for each of those. But if we look at the growth of the pattern in terms of the blue blocks, we can see that the growth is the same. But what's different is that constant is kind of almost like pushing that trend line up the graph. So I have a video now to show you. These are some really good questions to ask. What is similar about the rules? What is different? What is similar about the patterns? What is different? What is similar about the trend lines on the graph? What is different? Because that really pulls apart the responsibility of those two parts of the rule. The fact that the constant tells you where the line starts, or where it is on that vertical axis, and the multiplier tells you how steep that line is going to be. And a lot of times students conflate that. So for example, if you had times 3 plus 1 rule, and they graph that, and then if you ask them what would happen if it was a times 3 plus 5 rule, a lot of times students will say it will start higher up on the graph and be a steeper line. So they conflate those two. So this activity really allows us to pull apart the two parts of that rule. So I've got a video now of, these are 2 grade 6 girls who went through this process, and they talk about their original prediction.
Well, the lines are parallel to each other, and we knew that because the multiplication was the same.
And we knew that multiplication equaled how steep it was, so we predicted that they would all be the same. They would be parallel.
The same distance between them.
But they would have different heights, because one's plus 9, the other's plus 6, and the other's plus 2.
And also they would start at different points for the same reason.
Because 0 times anything is 0.
And so this was, well, for us it was our prediction, because we had to predict before, and again we knew because of the multiplication.
They were different multiplications. One, it'd probably go up like that, as Matthew said. But even if it was just times 4, it would still just go up a little more, because you're timesing more by the position on it.
Ruth, are you there? If you are there, I believe you might be muted.
Sorry. Okay, so what I was saying to myself apparently is that the thing I like about that video is it really shows how important that pattern building is as a bridge between the pattern rules and the graph. And so that they start to connect the value of the multiplier with the steepness of the trend line, the value of the constant where it starts on the graph. But without that Interim representation, that bridging representation of the actual physical patterns, that is the thing that allows them to make that connection. So we've got one more video to show you, but first of all, we've got another couple of rules, and this was actually a student-generated inquiry. So we've got number of tiles equals position number times 2 plus 6, and number of tiles equals position number times 3 plus 5. And I'd love you to think about what you think is going to happen with these rules. Some very nice predictions there. Okay, let's go ahead and watch what happened in the classroom with this student question.
Okay, so there's Naroshan's question for the class. Go ahead, ask it, Naroshan.
Me?
Yeah.
And that one was if everything was the same, right? This one was how about if everything was different, so the multiplication part's all going to be different, and the addition part's all going to be different. What would happen?
What do you think would happen? Okay.
Say that like this and I don't know about this line, but this and this line are going to intersect for sure because like times 3 plus 5 for 1 is going to be 8. Times 2 plus like this is going to be 8.
Okay, go ahead. Grab
And for number 1, and this is also going to be 8. So it's like going to be like. So the 0th position, it's going to be like 5 for this one and 6 for this one. And then this is going to be like 4, 7, 8. This and it's also going to this. It's
So
like
that
this.
line is going to go that way. Yeah.
Just
Keep extending the line.
So
Extending the line.
I think it's going to go something like this.
Yeah. So.
But I know it's going to intersect here for sure because for the position number 1, both answers are 8.
So he, just to recap his thinking, because it was so excited to be in the classroom to capture that. And then this was replicated in many, many other classrooms since then. So he says he knew that they were going to intersect for sure. And his way of thinking about it was for position 1, knowing that the two rules, if you were, say, thinking about building them as patterns, they would have 8 tiles at position 1. Or just thinking about their relationship, that each of them for position 1 would be 8 on the graph. And so the fact that he could then just extend those rules, like he had this really nice sense about how those trend lines would work on the graph, how they would cross over there, but also the fact that one would start higher but have a less steep slope, and one would start lower but have a steeper slope. So how some other kids thought about it is, again, they thought about it explicitly in terms of their pattern building, so visualizing what a pattern would look like and understanding that at position 1, they would have the same number of tiles. And so some kids were still thinking about it in terms of the visual patterns. Other students were thinking about it like that student just did, and thought about almost like the movement of the trend lines on the graph. So even though they're graphing static patterns, a lot of students started to speak about it in terms of movement of trend line on the graph, so that one would start higher but grow slower, and one would start lower but grow faster. So, which was really interesting to us. And then thinking about the fact that they're going to smack they're going to intersect at 1 and then keep going. So again, so thinking about the fact that we started off, with some really simple seeming kind of pattern building activities, and we can progress then to a point where kids can look at a pattern rule and start to visualize what that graphical representation is going to look like. And so that is it. Thank you so much. And if you would like any more information about this, there are some resources out there that support all of their learning we've done today. I feel like we've covered a lot in a very short space of time. So if you're interested in this work at all, there are some resources. There's the Paying Attention to Algebraic Reasoning from the ministry. There's also the math clips, which are online resources that really support this work. So if you go to the Math Clips website and look for the patterning in algebra, all of the work in there is supports everything that we've done this morning. Please feel free to email me if you have any questions. My email is on the final slide and also on the first slide. And thank you so much. I really enjoyed this, and I hope that it was beneficial for all of you.